Welcome everyone. This is chapter 24 of the Crystal Clear Electronics video series. This chapter of the curriculum is on control and regulation, which we will present in 3 separate videos. The chapter was written by Gergő Harangli, Csaba Apró, Máté Trádler, and Barbara Újvári. It was supervised by Ádám Szabó. Ambrus Zelei will be our presenter in these videos.
In this chapter, Zalán Gyuricza will help us to assemble the tools, operate them, and clearly explain the ins and outs. Zalán, please tell us a few words about yourself.
I am Zalán Gyuricza, a 4th-year electrical engineering student at BME. I work alongside the university, and my job is also my hobby, programming microcontrollers for different tasks. I became interested when I was 14 years old, and since then I've made a Wi-Fi clock with electron tubes, a digital schedule, an LED strip controller, a calculator, 2 model cars, and even a car diagnostic device. I also ride an electric scooter, which you can find here. It's also linked to today's topic, but we will talk more about that later.
Alright. Thank you for the introduction. And you may have seen me in previous videos, so I'll just say I have spent a lot of time around robots and controlling them. What exactly is a robot? Essentially, it's a mechanical device usually powered by electric motors. But not just in any way. They can gather information from the environment using sensors. Then, this data is transmitted to a computer where the robot's program runs, similar to what we saw in the microcontroller chapter. The program makes a decision and moves the robot's parts according to that decision. It is interesting to note that the way humans work is very similar to how robots do. We also have sense organs, a central nervous system, and a brain where we process the perception. Then, a message is sent from the brain or nervous system to the muscles, which triggers the movement of our limbs.
I have the feeling that this topic is very much related to control and regulation.
Yes, the disciplines of robot control and human motion control are closely related. I've brought a pneumatic robot as a demonstration device, which can control the position of the robot's arm. I can control 2 angles in total with this small pneumatic pump and switch. And why I say control and not regulate will be explained in this lesson, among other things.
That's right. So control and regulation are very common words. We're going to hear about them now in general and also in relation to electronics.
Yes, we also hear the word regulation in the context of, for example, laws regulating the way society works. And also in forestry, they also artificially regulate animal populations. The desire to influence and control what happens around us is a fundamental human nature. This human characteristic has manifested itself in many cases throughout history. When a country expands, for example, it means that it wants to control a larger area. Therefore, the case is that we only feel ownership of an object or a process if we can influence it, in other words, if we can control it. Another driving force behind the development of control is laziness. We want processes to run by themselves and to run as we predetermine. The word robot was first used in the 1920s in a play about human-like machines doing menial work. The word robot means slave labor. After all, it is derived from this word. Now let's move on to really focus on regulation in a technical sense. Let's look at the technical aspects. The steps for implementing a control loop are modeling, design, and finally implementation. By modeling, we mean that we are able to create a model that accurately represents the characteristics of a real-world process. By process, we mean a measurable physical quantity. For example, consider the DC motor, which can be found in this fan. You may have come across it in the previous chapters of the curriculum. The torque, the angular velocity, the current flowing through the coil, and the voltage of the coil are all considered processes. Each of these is measurable or derivable. The model used to describe the engine can give a mathematical relationship between torque, angular velocity, current, and voltage.
So we have a model to describe reality. And how would we explain the design process?
By design, we mean creating an algorithm, also known as a program, that keeps the process we want to run at the value we want. For example, if we want to keep the speed of the previously mentioned motor at 1000 rotations per minute, we expect the algorithm to keep the rotation per minute at exactly 1000, whether the torque load on the motor shaft is small or large. Of course, there are limitations, and we also need to know the characteristics of the motor well, so we need to have a good model.
So when designing, I figure out what should happen in a particular situation, and then I write an algorithm. And what does implementation mean?
That's a good question. By implementation, we mean the process of producing the algorithm in the form of a program code that can be executed by the microprocessor. After that, let's talk a bit about the control loops. We may already have an overview of how robots and the human nervous system work, but let's take a closer look at it. First, we must bring clarity to the elements that are involved with a control loop. There is always a process that we want to control. It means that there is a specific value, and we want to keep the process at that value. We call this the reference. For example, for a robot, let the process be the height of the end of the robot arm measured from the tabletop. Let's say the reference is 10 centimeters. That's where I want to keep the robot arm. We need to think of the reference as being able to take roughly any value, so we need a reference signal forming block that doesn't allow us to ask the control for an arbitrarily large value, and also generally limits the maximum rate of change of the reference signal. So, for example, the robot arm cannot be expected to jump 3 meters from this position in a tenth of a second.
But we need another device, a decision-making device, don't we?
Exactly, but more on that when we compare open and closed loop control. There must be a control device in the loop that enables us to be able to affect this process. This is necessary because the control algorithms are running on the microcontroller. As it has been noted in the previous chapters of the curriculum, the microcontrollers have 3.3 volts or 5 volt peripherals. Such an output is insufficient for driving an electric motor. So the actuator's job is to convert these weak signals of the microcontroller to strong signals, which is capable of driving a motor.
So for the robot, the actuator is the signal amplifier and the electric motor, which then generates a torque. Or here, in a pneumatic robot, the actuator is an air-driven working lever that generates force.
In most cases, the microcontroller or a large computer is the control unit in the system. Its function is to run the control algorithm and decide what kind of control signal to generate for the actuator based on the input. There are numerous benefits of using a microcontroller, as they can be easily reconfigured and we can modify a parameter in it even while the program is running. Furthermore, with the increase of their computing power, number, and complexity of their peripherals, they can run almost any algorithm.
And why do we only use a microcontroller or computer in most cases? What other solutions might there be?
Good question. There are analog control loops whose control system is not programmable and the signals in the system are not digitalized. Their presence is mainly restricted to special areas. If high speed is required, analog circuits are mostly used even today. Since most engineers are visual types, many schematics and illustrations are used in the field of control engineering to help understanding. The diagram containing the control elements and their logical relations is called the block diagram, which helps understanding the operation and the function of each block. Based on what we have seen so far, I think you can already guess that in terms of operating principle, there are two types of control loops: open loop and closed loop. You will soon see a block diagram for both.
That's true, but more on that in the following video. For now, we thank you for your attention and encourage you to keep it up.
Please remember that the chapters of the curriculum build on each other. So if there's something you might not be familiar with, you'll probably find it in an earlier video or earlier chapters of the written curriculum. Thank you very much for your attention. Bye bye!
Bye!